This video is going to discuss setting up surface integrals. I hope you've watched the previous video on the surface area, whether the surface is described parametrically or as the graph of a function of two inputs. If you've watched that, we've done all the hard work there. This is just going to show how things sort of fit in a slightly more general framework. So let's revisit the surface we saw earlier. This was the sideways paraboloid. We're going to set up three integrals, one for the surface area, one to just integrate this given function, f of x, y, z is equal to y plus z quantity squared, and then finally one integral which will represent the mass of the surface if the density is given by rho is equal to x over the quantity y plus z. So this is all from before, so I won't repeat through all this. The only new thing we're really going to need is that ds is just given by this norm of the cross product of RU and RV. Sorry, there's typos here. Those should be V's. Just with a du dv or a dA afterwards. And here's the area. The difference from the version you have seen earlier is that there's a ds here instead of the entire thing dA, and that there's this inclusion of a 1, but you could of course exclude the 1. The whole point of the 1 is for emphasis because you can also look at the integral over the surface S of now the function f. And the way that these are related is, well, if f is just the constant function 1, then you get the area. If you instead integrate this function y plus z quantity squared, you've got to place that right here. The thing is, this is an integral with respect to u and v, so having just y plus z quantity squared here is not so helpful. You just need to replace, remember from the parameterization, y was equal to 9 minus u squared and z was equal to u sine of v. If you want the mass, this is really no different, at least as far as technique goes. This is really just a word problem version of this. It's just the function that you need to integrate is no longer called f. It's just the density function. So instead of f ds for the integral, you have rho ds, and you just put the rho right over here. But again, having rho in terms of x, y, and z is not so useful for integrating, so you just steal from the parameterization. I just wish to highlight in red that all you're doing is really integrating a different function, whether that's 1 or the given function f or some other given function rho over the surface, and the ds in all cases turns into what you see in blue over here. That was the norm of the cross product of r sub u and r sub v and a dA afterwards. The other surface we looked at in a previous video was a surface that was just really given as the graph of this function g of xy equals x cubed times y to the 7th. So this was, we're going to look over, that surface goes forever, so we're just going to look x between 1 and 8 and y between 2 and 9. So this is a square, right? You're just looking at every point above this square of side length 7 in the x direction and in the y direction. And we'll set up the same integrals again. Okay, we'll set up an integral for the surface area, one to integrate this provided function f, and one to integrate over this other provided function rho, and that will represent the mass since rho represents density. This is all a repeat of what you've seen before. I'll just point out then that ds here is, well, quite naturally, if this was the cross product of RU, RV, then you have that with a dA after, although the dA is now a dx dy or dy dx instead of a du dv or dv du. So now the setup of the integrals, just like before, the area is going to be integrating 1 ds over s, and so then over here you see bounds for d, the parameter domain, and here you have an s. If you're instead going to integrate the function f, that's fine. There was this provided function. The thing is, the provided function has a z in it, and this is a dx dy integral, so we just replace the z with, well, this is the definition from the function, so x cubed times y to the 7th. And finally, if we use the density function, we're going to integrate the density function rho equals x over y plus z. Same thing, just replace the rho here with rho, but putting the z in here is not so useful, so we just replace the z with its definition. Z is equal to x cubed y to the 7th. Think about how this really literally is the same thing you'd get if you had just parameterized the surface S using the variables u and v instead. You would have r of uv is equal to u comma v comma u to the 3rd v to the 7th. So then this integral is literally what you'd have set up. It's just all the x's here would be u's and all the y's here would be v's.